Hi. So we'll start our lecture today by Simon Glover on numerical simulations of galactic scale interstellar medium. Take it away.
Okay, thank you. So in keeping with our focus this week on tools, I'm going to talk to you about one of our most important theoretical tools for studying the interstellar medium, which is the use of large numerical simulations. And the focus here is on what I've here called galactic scale. So what I mean by that is reasonably large scales within galaxies, so kiloparsec scale or larger, often with resolution to resolve down to parsec scales. But the focus here is not really on modeling star formation in individual clouds. It's more kind of understanding how the ISM in representative patches of galaxies work. A lot of what I'm going to say would also hold for studying star formation in individual clouds, but some of the focus is slightly different. And what I'm really going to try and talk to you about today is how we do this. What are the physical ingredients you need to put into these sort of simulations? How can you actually do this numerically? What are the sort of trade-offs and caveats you need to be aware of? And then with a little bit of focus at the end on just giving a few examples. But I'm mostly not going to be talking about what we can use these simulations for, the science that we get out of them, because this is something that Eric Emsland is going to talk about next week in his lecture. So today is really about the how, and his lecture is going to be about the why and what we learn from that. What I'm also going to say is, like, for many of the topics I'm going to talk about today, I'm only going to be able to give a very broad overview. A lot of these, I could easily spend an hour and 45 minutes just talking about one particular thing, like how to best model chemical rate equations on computers. So anybody who's interested in learning more about any of these topics in depth, just come and talk to me afterwards, because we can't, there's just not time to do everything in full detail today. Okay, so let's get started. What are the physical ingredients that we need to worry about when we're trying to simulate a galaxy? Well, the ISM is made of gas, primarily. So the obvious starting point is, how do we model gas on computers? How do we model hydrodynamics? This is 99% of the ISM. The dust and the cosmic rays are a tiny fraction of the mass. So any model of the ISM needs to account for how gas flows. These are the equations of fluid dynamics that we normally use. So the Euler equation for the momentum, the continuity equation, and the standard energy equation. And our first choice that we have to make when we want to solve these is, how do we actually represent this on a computer? We can't solve these analytically for the general case where we have complicated gas flows. So we need to solve them numerically, which means we need to actually discretize them. We need to break up space into a series of resolution elements and solve these equations on this set of resolution elements. So how do we do that? Well, there are basically fundamentally two different types of scheme for doing this, which correspond to our two different ways that we can actually write down the fluid equations. We can write them down in an Eulerian perspective, which I've done here, where we're dealing with a coordinate system which is fixed in space. So our observer is fixed at some point in space and looks at the flow of fluid past them. So this is, in this little picture, this is this idea. We have some control volume that's fixed in space, and we see how gas is flowing in and out of that volume and how the variables within that volume are changing. The other picture that we can have is the Lagrangian picture, where we're actually imagining moving with the flow. So our control volume in that case is flowing along as the fluid flows. And so then we just actually move along with the fluid and look at how the other variables change as we move with that fluid. So we can basically discretize flows in two different ways, depending on whether we adopt an Eulerian perspective or a Lagrangian perspective. So for the Eulerian case, we have some spatial grid which is fixed in space. It's commonly a Cartesian grid, but not always. Sometimes it's more convenient to take something like cylindrical polar coordinates or spherical polar coordinates. For instance, if you're modeling something like an accretion disk, cylindrical polars are often a much better choice than Cartesian coordinates. And then we define values for the fluid variables in each of our cells, and we look at how fluid flows in and out of each cell and how that causes our variables to alter. In the Lagrangian case, we instead represent our fluid by some set of Lagrangian fluid elements, which could be grid cells or could also be particles, which I put in inverted commas because these are not particles in our normal like microphysical sense. These are kind of representing actually large amounts of fluid, so many actual physical particles. Now, these elements move with the flow, and hence, in any kind of complex flow, they will tend to not just change their position, but also their size and shape. But they will conserve the total mass. So, sorry. Now, the simplest case for an Eulerian discretization is we just have some fixed grid. We just put down some uniform fixed mesh. This is nice and easy to do. Codes that do this have been around for a very long time. The downside is, of course, that this has a limited dynamical range. The smallest thing we can represent is limited to the size of a grid cell, and there are practical limitations on how many grid cells per dimension you can actually afford. I think the largest simulations, for instance, of compressible turbulence in an astrophysical context are something like a few thousand cubed, which is already a lot, but that's only a it's only a dynamical range of a few thousand. And this can be a problem if we want to study the ISM, because structures in the ISM cover a very broad range of scales. If we want to model entire galaxies, we need to deal with scales of tens of kiloparsecs. Even if we're just interested in representing bits of galaxies like the central molecular zone or a spiral arm, we're still typically dealing with structures on the scale of a kiloparsec. And yet, if we want to model individual prestellar cores within clouds, these have scales of much smaller than the parsec. So this is a broad range of scales, and you can't really represent this on a single fixed mesh. So in the Eulerian picture, we can confront this problem by basically refining our mesh using what we call adaptive mesh refinement. So the idea is where we need more resolution, we just make our grid finer. We put in additional smaller scale grids just in those regions. And because we're not doing this everywhere, we can afford to get a much larger dynamical range for a reasonable computational cost. And adaptive means we do this as we go along. We don't decide ahead of time where to put these fine meshes. There are also approaches where if you know for sure where you're going to need the high resolution, you can just ahead of time decide, okay, I'll set my refined grids up in these places. This, for instance, can be very good if you're just looking at like the collapse of a single prestellar core to form a star, and you know you're just going to need the high resolution in the middle. Then you can say ahead of time, okay, I'll just use some nested grid and put the high resolution in the middle. But in a galaxy, we don't know ahead of time where the clouds are going to form, so we need to adapt the mesh as we go. We define some refinement criteria which tell us, okay, if the density goes above a certain level, or if our gene's length drops below a certain level, then we put in a finer grid. And what you get after a while of doing this is a picture that looks something like this. So you see, if you look carefully, where we have higher density, so the darker colors, we have a finer grid. Where we have low density, we have a relatively coarse grid. And this means we can just spend our computational effort resolving the places where interesting things are happening, and not spend a lot of computational effort on relatively low density regions where not much is going on. Okay, so the advantages of this approach is that the grid structure is relatively simple. I mean, the fixed Eulerian grid is extremely simple, but even the AMR grid is relatively simple. We know what our neighbors are. It's relatively easy to implement new physics in Eulerian codes. Another advantage, which is perhaps a bit less obvious, is you can get good resolution even at low densities, because our minimum resolution is fixed by our coarsest grid. So as long as we take that to be reasonably fine, then that is the worst we're going to get. And as we'll talk about in a minute, this is not the case when we use Lagrangian methods. Now, the disadvantages, often the AMR approach is more costly when we want to go to high resolution or high dynamical range than the Lagrangian approach. This is because every time we refine, we're putting in a new grid, and often that actually is covering more volume than the region we're actually interested in. We don't have such fine control over how much refinement we do. Another important disadvantage when we're trying to model something like a galaxy is that the AMR approach is less accurate for representing large-scale bulk flows, so something like galactic rotation. And this is because every time fluid flows from one cell to another, we're introducing a certain amount of error into our solution. There's an inherent truncation error in any numerical solution of our fluid dynamics equations, what we call advection error. And this gets worse the larger the velocities are. And if we're having to represent a bulk flow, then you potentially have lots of this flow from cell to cell in an Eulerian code. So lots of opportunities for errors to come in, which you can avoid with the Lagrangian method where your entire grid is moving at that bulk velocity. So examples of codes that work along these lines. There's just two examples here, which I'll show results from later on. So one is Flash, and another one is Ramses. So the folks in Project 9 will have already been using Ramses also in AMR mode to do relatively simple simulations. I'll show later on some results from much more complicated galactic scale simulations. Okay, now what about Lagrangian methods? So the main true Lagrangian method that's used is something called smooth particle hydrodynamics. And the basic idea of this is we're modeling the fluid with a set of particles with fixed masses that move along with the flow. So they're local. The velocities of these individual particles are set by the local fluid velocity, and then we calculate quantities like the fluid velocity or the density or the temperature by averaging over a set of particles. So we define what's called a kernel function, which looks a bit like this. And essentially, to get the values of any physical quantity at some point, we just sum over the values carried by the individual particles with a weighted sum where the weighting factor is this kernel function. Now, in principle, you would want to sum over every single particle in your simulation to get the most accurate results. In practice, you don't do that because that would be ridiculously expensive. So in fact, these kernel functions generally are defined to have what's called compact support. So they only extend out one or two smoothing lengths, where the smoothing length h is, you can think of it a bit like the standard deviation. It gives some sense of the size of this kernel function. So it's the equivalent of the grid cell size in an Eulerian code in terms of our resolution. Okay, so the advantages of smooth particle hydrodynamics. In its most basic form, it's a very simple code to implement. You can write your own SPH code relatively easily. I don't advise doing it because to get it to do interesting things, then that takes a while. It's mesh-free. This is good because then you don't have artifacts relating to your grids. As those of you who have already played around with the Ramses simulations, looking at the set of point explosion, you'll have noticed that it's not very spherical at low resolution. You get these features that are aligned with the grid. This is a quite common feature of grid codes, that if you have a predefined grid structure, that this introduces more error in flows going along the axes of that grid than at right angles to or at other angles. So you have some artifacts that just arise from the grid structure. From something like SPH, you have no grid, so you don't have any of those artifacts. And you can also show that angular momentum exactly conserves both linear momentum, which is relatively easy to do, but also angular momentum, which is harder for grid codes to do. The disadvantages of SPH, and there are several, plain SPH has a limited dynamical range. It does better than a non-adaptive grid code because it's Lagrangian. It's automatically following the fluid. But because the particles have fixed mass, it has a fixed mass resolution. So once the object you want to study has a characteristic mass that's smaller than your particle mass, or smaller than a small multiple of your particle mass, then you're going to be in trouble. There are techniques you can use to try and get around this. The most common is called particle splitting, but there are a whole load of issues that come in once you start splitting up particles and having SPH particles of different masses interact, and it introduces a load of noise. It can be useful in its place, but it's not very reliable. A second disadvantage of SPH is to actually get the right solution. You need, at the very least, artificial viscosity to damp out oscillations that would otherwise be created, which would be completely numerical. And in some cases, you also need other artificial terms, like an artificial thermal conduction term, so that you actually get the right solution. And you also run into situations where the behavior you get can depend on the choice of smoothing kernel. Like for certain types of kernel, you can get what's called tensile instability, where your particles just like to clump together completely numerically and no longer properly represent what the underlying fluid is doing. So examples of codes using this that have been used for galactic scale simulations are Phantom and Gadget. And then we also have what are called mixed methods. So these have become popular within the last 10, 15 years. So the idea here is to try and combine the strengths of the Eulerian AMR approach and the Lagrangian approach into a single code. And there's two main codes that are used for galactic scale simulations that do this. There's a repo, which is using a moving unstructured mesh. And then there's GISMO, which uses a mesh-free quasi-Lagrangian approach, which differs a little bit from a repo. So first, a repo. The basic idea here is we define a set of sample points that move with the flow. So you can think of these being a little bit like SPH particles, but not quite. And then we define a mesh, which is just the Voronoi tessellation of these points. So that for our sample points in red here, the Voronoi tessellation is shown in black. So this is just a 2D slice. But of course, you can do this in 3D. And then the flow variables within each cell are just mass-weighted averages over the cell. Okay, so why is this a good thing? Well, using this scheme, we can avoid the mesh getting horribly distorted if we have a very complicated flow by applying corrective velocities to our mesh generating points. So the idea is that this is not a completely Lagrangian code. Our points mostly go with the flow, but if we see that the grid is getting too distorted, we can nudge the points a bit to keep the cells more or less round. This cuts down on the advection errors from cell to cell and avoids a lot of the problems that fully Lagrangian mesh codes have had in the past. The downside is, because this is no longer a fully Lagrangian code, you have to compute mass fluxes in between cells. So you need to kind of take your variables defined at the center of the cell, or the center of mass of the cell, and work out what the variables are actually at the face in between two cells, and then use that to work out the flux of mass and momentum and energy and any other quantities of interest from cell to cell. And this is quite complicated. Do not ask me in too much detail about how a repo actually does this, because it's scary code. So advantages of this approach. It's Galilean invariant, as SPH is. So this means it's a good choice for a problem with high bulk velocity. You don't get lots of error introduced just because your flow is going fast if it's all going at the same velocity. It's very adaptive, and it's adaptive in a way that's more efficient than an AMR code, because we can just add individual mesh points to refine individual cells. We don't have to put down an entire finer mesh. If we want to refine, we can just add a few additional points or remove them again to de-refine. And in practice, it's used by a lot of people, and there's a lot of interesting physics modules available. Now, the disadvantages, as I say, the grid calculations and flux calculations in the repo are quite complicated. It's a pretty complex code. This can make it difficult to add new physics. It really depends a bit on how much it needs to interact with the grid and the Riemann solver, and how much it's just a separate module doing something simple. So putting in something like chemistry is relatively straightforward. Putting in something like radiative transfer, where you really need to understand the grid structure of the grid, is complicated. The other big disadvantage, of course, with a repo is it is a private code. Although a lot of people use it, you have to go and ask Volker Springel for permission. There is a public version, but the public version doesn't have most of the interesting physics in it. It has the basic hydro, gravity, and a few other things, but a lot of the stuff that we're actually interested in for modeling the galactic scale ISM is not in the public version, which is a shame, but this is not something I have any control over. Okay, so what about GISMO? GISMO uses a scheme called the meshless finite mass scheme. So again, this defines a set of sampling points which move with the flow. But now, instead of defining a Voronoi mesh cell, it instead partitions space amongst the particles using some weighting function. So in cases where the weighting function assigns all of the volume of space to the closest point, this just gives you a Voronoi mesh, and you recover the repo scheme. But in cases where the weighting function actually says, okay, we will assign most of the weight for this point in space to the nearest particle, but then we'll assign some weight to slightly further away particles, then this is the MFM scheme. And so basically what you wind up with is a Voronoi mesh with slightly fuzzy borders. So this would be the repo case. This is SPH, where we have a spherical kernel, and this is MFM. So the particle velocities can then be set to match the fluid velocities, and we can solve for the fluxes between the volumes assigned to the different particles. Now, the advantages of this compared to the other methods I've been talking about, again, it's Galilean invariant, it's highly adaptive, good choice for when you've got high bulk flows or high dynamical range. Compared to a repo's Voronoi approach, it has a lower memory cost because it doesn't actually construct a mesh. It just has this weighting function and this idea of like each point in space being associated to a particle, but it doesn't have to carry around lots of information about where the boundaries are between different mesh cells, because it doesn't have a mesh. And this can also make it go somewhat faster than the repo. And GISMO also has a lot of physics implemented for it. So like projects like Starforge and Fire use GISMO. Disadvantages, as with the repo, it's a complex method. It's a lot harder to get your head around what it's actually doing than in an Eulerian code. And again, the public version has most of the interesting stuff taken out of it. Okay, so much for hydrodynamics. But as we all know, the ISM is actually magnetized. It's a charged fluid, although it's electrically neutral overall, and electric fields are not important. We can have current flow, so we can have magnetic fields. And so we should actually be solving the MHD equations when we're modeling the ISM and not the pure hydrodynamics equations. Now, in principle, it's easy to introduce the relevant additional terms into the fluid equations, into our discretization. The main issue that we face when we do that is, what do we do about div B? We know from electromagnetism, div B should be 0 everywhere. Like, that's one of Maxwell's equations, div B equals 0. There's no magnetic monopoles. But numerically, this isn't always guaranteed to be the case, depending on how we discretize the MHD equations. You can use schemes which by construction, make sure that div B equals 0. So an example of this is the so-called constrained transport scheme. But it's not always practical to do this. For instance, there is an implementation of constrained transport in the repo, but it only works when all of the grid cells in a repo are running on the same time step, which in a Galaxy simulation basically means your entire hierarchy of grid cells is running on whatever time step your smallest cell is running on, which is generally quite short. So you can use it, but it does not do good things for your efficiency if you're doing very adaptive simulations. And so sometimes we can't do that, and we have to use a scheme that does not numerically enforce div B equals 0. So what do we do in that case? The next best option is something called divergence cleaning. And the basic idea is that the code identifies regions where div B is very non-zero and tries to damp those errors and also propagate them away to the edges of the simulation volume. Now, this is a widely used scheme. A lot of the simulations that we'll be seeing later on use some form of divergence cleaning scheme. And it can be very effective. The main thing to worry about here is you need a time step limiter along with this, because you need to make sure that your growth in div B is getting damped fast enough to stop your solution from blowing up. If div B is growing faster than your divergence cleaning can get rid of it, then sooner or later, all hell is going to break loose and your simulation is going to crash. For instance, some colleagues of mine are currently doing some code comparison problems trying to look at the launching of a magnetic jet in a collapsing prestellar core. And if you have too large a div B, what can happen is as your core collapses, suddenly the dense part jumps out of the center of the simulation because of the div B error. So yeah, this is one of the things that numerical astrophysicists generally don't like to talk about, but you should be aware of when you're dealing with any kind of MHD simulation. Like, how are they dealing with div B, and are they sure that it's actually getting damped fast enough? Okay, other issues. In principle, we may need to deal with non-ideal MHD when modeling magnetic fields. In practice, for the sort of simulations that I'm mostly focusing on, these galactic scale ISM ones, this is generally not going to be important. The ionization is generally high enough that the non-ideal effects are small. But if you want to look at, for instance, the formation of individual prestellar cores or their evolution, then you can get to a regime where actually effects like ambipolar diffusion or ohmic dissipation become important, and then you actually do need to start worrying about non-ideal MHD. A more pressing issue for galactic scale simulations is what initial condition do you start with? Do you start with a very weak magnetic seed field and let the dynamo amplify it and produce a kind of self-consistently grown field, which presumably gives you a better match to what's actually going on in the galaxy at the cost of needing to run your simulation for a lot longer? Or do you actually start with some prescribed field strength and geometry, in which case you need to figure out what those are? And you may well find that the choices you make there influence what your simulation later on does. And then finally, there's the issue of what do you do with B when you form stars? If you remove gas from your grid and turn it into stars, but you don't remove the magnetic energy, then if you're not careful, this can locally give you a decrease in this so-called plasma beta parameter. So this is the ratio of thermal pressure to magnetic pressure. So if you remove a lot of gas and don't remove the field, then locally you get dominated by magnetic pressure, where physically you probably shouldn't, because a lot of that field actually physically will have gone into the stars themselves. This is one of the bits where nobody really has a good way of treating this, so we just generally pretend it's not a problem. Okay, so that's hydro and MHD. Now, the next big thing we need to worry about is, of course, gravity. If we want to actually form a galaxy rather than just a big blob of gas which is going to explode, we need some kind of gravitational force to keep the gas together. Gravity, in principle, is very simple to solve. It's just an inverse square law, and we know where all the mass is. But of course, the trick with gravity is to do this in a computationally efficient fashion. The easy way to do this, which is for each cell, just go to each other cell, work out its distance, work out the gravitational acceleration due to its gravitational attraction. This does not work well for large simulations because this so-called direct summation scheme has a cost which scales as the square of the number of resolution elements. So for very tiny simulations with n of like 10,000, that's fine. But for simulations with n of 100 million, this is not fine. This is far too slow. And so most ISM simulations instead use some more approximate scheme to avoid this cost. And the most common way to do this is with what's called a tree code. The basic idea is that you group together particles or fluid elements which are a long way away and treat them all as if they were in the same position. So for that whole group of elements, you just have to do one calculation. And then you only do the individual direct summation for things that are very close to you. So if you do that, you find that the error depends on the size of the group versus, I mean, size in the sense of the separation between the members of the group versus the distance to the group. And if you make sure that that ratio is small, you can make the force errors small. So the idea here is you can split up space into a hierarchical tree. So this red point is the point where we're wanting to work out the gravitational accelerations. So for mass that's a long way away, we can just look at these big groupings, take all of the mass points within this cell of the tree and put it at the center of mass and just work out the force due to that. Whereas for things that are closer to the point we're interested in, we need to look at the lower levels of the tree until within one of these cells, you're actually just doing direct summation. So I'll skip over that. Now, the different types of tree exist depending on how you construct it. For instance, binary trees, oct trees, but the basic idea of all of these is the same. And the computational cost you get with all of these is also the same. These give you a cost which scales as n log n rather than n squared. So obviously for large n, the difference between n and log n is enormous. And so this is why we do this. The disadvantage is, of course, doing this is more complex than dealing with direct summation, particularly when you're dealing with a code which is running on multiple CPUs, and you are giving up a bit of loss of accuracy. So we do this when we have to, but for like small n systems, if you're interested in just like the interaction of a small cluster of stars that you form within a cloud, you might well use a direct summation solver to do the individual interactions of those stars and only worry about using the tree for the larger scale gravitational influence of the gas. Okay, but in principle, all of that's straightforward. There's not too much to be aware of there. A more subtle issue is gravitational softening. So gravitational softening is basically adding in an extra term into the denominator of our force equation, this softening term. So this is the simple example of Plummer softening. And the idea is that we want to avoid getting very high gravitational accelerations on very small scales. Now, there are two reasons for this. One is computational. If you get very high accelerations, then you get very high velocities, and so your code goes very slowly. And second, on small scales, we don't expect the mass distribution to be properly modeled anyway. Once we're down close to the resolution scale of our simulation, there's a limit to how much accuracy makes sense. If we don't actually know to within better than the size of a grid cell where the mass is, then assuming that we know it exactly is actually wrong. So it's common to use this kind of softening. Now, this softening length can be set explicitly, or it can be related to the local size of your fluid elements, for instance, the SPH smoothing length or the local grid cell size. In cosmological simulations, it's quite common to just take a fixed minimum softening length. The reason for this is that doing this allows you to conserve energy if you don't have any dissipative processes. But it turns out this is not a good choice when dealing with self-gravitating gas. And we've realized for a long time that once you have gas and self-gravity, it's important to make sure that the gravitational softening and the inherent smoothing of the pressure gradient you get due to your limited resolution match. And if they don't, if you're softening gravity more than the pressure or softening pressure more than gravity, you can either get artificial fragmentation or artificial suppression of fragmentation. And this is a point that I think a lot of people don't appreciate. You really need to be careful that you're smoothing both forces on the same scale. And so whatever you are taking for your softening in any simulation involving gas should match what your minimum resolution is for the gas itself. If it doesn't, you will get the wrong behavior on small scales if you have self-gravitational effects becoming important. Okay, a related issue is just the resolution we need in order to actually follow gravitational fragmentation of self-gravitating gas. So the characteristic length scale here, as I'm sure you're all aware, is the Jeans length. So this is the minimum length scale on which a perturbation in a self-gravitating gas becomes unstable. So it's the length scale basically on which gravity and pressure balance. Anything larger than the Jeans length will inevitably collapse. Anything smaller will be pressure supported. And about 20 years ago, there was a fairly influential paper by Trulov et al. Who showed that in order to get well-behaved results in collapse problems, you needed to always ensure that this Jeans length was resolved by enough resolution elements. So they found that you needed at least 4 resolution elements per Jeans length. In practice, people tend to use somewhat more than that because 4 is a bit marginal. And this has become known as the Trulov criterion. And what happens if you don't satisfy the Trulov criterion? So if you have 1 cell per Jeans length in some collapsing filament problem, you get a whole load of artificial fragmentation. Yeah, you're unable to properly resolve the pressure gradients, and so your gas just breaks up into a load of blobs when it shouldn't. And you see, as you increase the number of cells per Jeans length, so this is 2 per Jeans length, 4 and 8, you get a better and better representation of what's going on. So with 2, you're still getting some unphysical clumping. With 4, it's mostly gone, and 8's even better. And basically, you want to take as many as you can afford, but of course, the more cells per Jeans length you take, the slower your simulation is going to go. So there's always a bit of trade-off between doing a good job of modeling the collapse and just having something you can actually afford to run. Okay. Still on the topic of gravity, we've mostly talked about self-gravity so far, but in most galaxies, the gas is only part of the mass. In fact, it's often only a small fraction of the total mass. So we also need to worry about the other mass components, the stars, the dark matter. In some cases, if we're interested in gas flows in the center of the galaxy, we need to worry about the central supermassive black hole or the nuclear stellar cluster. So how do we do this? Well, when we're dealing with very young stars, we'll often just track those explicitly with star particles. But we don't want to do this for every single star in the galaxy. We don't want to do this for the dark matter, ideally. So what do we do there? Well, there are 2 main options. We can, in some circumstances, explicitly follow the dynamical evolution. So really just put in a load of star particles to model all of the stars, put in a load of dark matter particles to model the dark matter, and then let them do what they want to as we run the simulation and as they feel the gravitational forces of the rest of the mass. So this is the so-called live halo approach. And people have done this somewhat successfully, but it's a bit costly. What's often done instead, and what's a lot cheaper, is actually just prescribing ahead of time the spatial distribution of these mass components. So if we want to model something like the Milky Way, saying, okay, well, we know what the stellar distribution of the Milky Way is, we know where the bar is, we know what the rotation curve is that we have to match. So we'll put in a mass distribution that represents that. And since we're not actually letting that mass distribution evolve, we don't actually need to put in mass at all. We can just compute ahead of time what the acceleration is going to be per unit mass as a function of position, and just tabulate that or express it as some function. And then on any time step for any cell, we can just go and like either look it up from our table or evaluate our function and say, okay, this is my acceleration due to this fixed mass distribution. This is done because it's very computationally efficient, rather than doing an n log n calculation for all of these gravitational forces from these components. You are basically doing an order n calculation, because for each resolution element, you just need to do one lookup or one function evaluation. And it's also often used because it's a good choice if we're trying to represent a specific galaxy, because we really have a lot of control over what those gravitational forces look like. So we can really, for instance, set up the potential to exactly match the Milky Way or exactly match some other galaxy we're trying to simulate. This is something that Eric might talk about a bit in his lecture, because he's been trying to do things like this to model individual galaxies from the FANG survey. I don't know if he's actually going to touch on that though. So now, how we do these models can be very simple. Like the simplest case, we have a bulge, a disk, and the dark matter halo, or we can get a lot fancier. We can put in things like the nuclear stellar cluster, the bar, the spiral arms. Sometimes this doesn't matter how we do this. Sometimes it matters a lot. Basically, what we generally find is if we're interested in gas morphology, then the details of this potential matter. But if we're just interested in something like how quickly the galaxy is forming stars, then it doesn't make much difference. So this is some examples from a recent paper by Yuni Gulla. So this is two sets of simulations. The top one is using a potential designed to match the potential of the Milky Way. And unfortunately, you can't see very well. But if you look at the center of the galaxy, you'll see that the gas distribution is clearly non-axisymmetric. You see a strong imprint of the bar on the central gas distribution. On the other hand, with just what's called a flat potential, so something that represents the Milky Way rotation curve but doesn't have features like the spiral arm or the bar, you get a more axisymmetric solution. Now, interestingly, you see also in both cases, you get spiral arms. In this case, we put a spiral arm feature into the potential to represent the stellar spiral arms. Here, there isn't. Here, there's just an axisymmetric external potential, but you get spiral arms anyway because these are gravitationally unstable gas disks, and spiral arms are a generic feature of those disks. Okay, now if we look at something like the star formation rate over time, this is what you get in these sort of simulations. And you see if we compare the Milky Way version with the flat version, so the black and the purple curves, there are some differences, but they're relatively small. There is a bigger difference between whether we're doing a pure hydro or an MHD run than between the runs with two different potentials. Okay. So we've talked about hydrodynamics, we've talked about gravity. Now, once we have self-gravitating gas, we know that sooner or later gas will collapse to very high densities and it will form stars. So what do we do in that case? What happens once gas collapses to a point where we can no longer computationally afford to resolve its Jeans length? Well, one thing, we can stop the simulation. Sometimes that's the right choice if we don't have enough physics in to really follow what happens later. But more commonly in these sort of galactic simulations, what we do is we allow stars to form. So we try and represent that numerically. And there are actually a wide variety of different star formation algorithms. So the simplest idea is just a simple density threshold. You say, okay, gas that's gone above my star forming threshold will get converted to stars either instantly or on some time scale, depending on the local density or depending on some other function that I prescribe. More complicated versions of this don't just put in a threshold in density, they also look at things like the molecular hydrogen content. This is quite a common idea in cosmological simulations of galaxy formation, where you only allow stars to form in molecular gas. Or you can also look at the temperature, and this is to avoid trying to form stars in gas which has just been shock heated. So it might be dense, but it's at 10 to the 6 Kelvin. That stuff shouldn't be forming stars. Now, these are all pretty simple to implement numerically. The main disadvantage is that there's no guarantee that the gas you're making stars in is actually gravitationally bound and collapsing. So generally, it's safer to put in at least some checks of this. And the most common ones are checking that the total energy, once you account for the gravitational energy, is actually less than zero, i.e. the system is gravitationally bound. Checking that it is actually collapsing, which you can do by calculating the velocity divergence and making sure that locally it's negative. Checking that it's actually accelerating inwards. This is quite a common one as well, where you do that by looking at div A. There are additional ones as well. For instance, you can check that your cell where you want to form stars is actually at a local minimum in the potential. That's also quite commonly done. You can basically make this as complicated as you want, with the trade-off being the more complicated it is, the slower it is. Anyway, supposing you decide gas should still form stars, how do we do this? Well, we can instantly convert it to a collisionless star particle, or we can convert it over some longer time scale or with some prescribed efficiency. So what's quite often done is that we basically, for gas which we declare to be star forming, we give it some probability of forming stars per unit time based on the local freefall time, such that if you wait for an entire freefall time, the probability is 1, but if your time step is much shorter than the freefall time, then your local probability is just like the time step divided by the freefall time. Or you can actually prescribe some star formation efficiency. You can say, okay, within one freefall time, I should convert 5% or 1% of my gas into stars. Or you can do what is common in simulations of star formation of individual clouds and convert it to a so-called sync particle. So for star particles, these are basically just collisionless particles. They interact purely via gravity. Once we've made them, they just feel the gravitational forces and can be sources for feedback, which I'll talk about in a minute, but they don't feel any hydrodynamic forces anymore. They're no longer part of our hydrodynamical calculation. And commonly, their mass is fixed at the point they form. So we form them, they're done. Now, depending on the scale of our simulation, these may represent individual stars, or far more commonly, they actually will represent clusters of stars. For instance, if you're making star particles with masses of 1,000 solar masses, these are not 1,000 solar mass stars, these are 1,000 solar mass clusters, which may have multiple O or B stars associated with them, plus many small lower mass stars. Now, depending on your masses of the star particles, it can be easier or harder to make sure that the stars you're forming actually properly sample the IMF you're assuming. I mean, first of all, you generally have to assume some IMF because we don't have the resolution here to model it. But you will then need to make sure you're properly sampling it because the obvious approach is generally the wrong thing to do here. If your star particles are very big, so they're all representing, say, 10,000 solar mass clusters, then you can just sample within each one from an IMF. And then when you add up all of the star particles in the galaxy, you'll get the right galactic IMF as well. If your star particles have 10 solar masses, and you try that trick, it doesn't work, because by construction, you will never form any stars more massive than 10 solar masses. So as you get higher resolution and form smaller and smaller star particles, you have to start being a bit clever about how you actually sample from your IMF. And you can do tricks like actually forming some star particles which represent more massive stars at the cost of then later not forming star particles for a while. So that overall, in the end, you still get the right IMF. There's a lot of fairly nasty details into how you do this. This is one of the regions that's quite easy to get wrong. Okay, or we can avoid that and we can make sync particles. So sync particles, again, are collisionless particles. Their main difference from star particles is their mass is not fixed. They can continue to accrete gas from the grid. They can continue to grow as they evolve. And again, these can be used to represent individual stars or clusters. This is the most common choice when you're like modeling individual star clusters within some GMC. Because then you can use sync particles to actually represent individual protostars where we do actually want to follow their mass growth. But we can use this on larger scales in galaxies as well. And again, we need to be careful with IMF sampling. Another issue with sinks, if your star formation efficiency on the scale where you're putting in the sinks is not 100%, then some of the gas accreted by the sinks is never actually going to form stars. And you need to account for that. And if you don't account for that so-called trapped gas, then you can get very wrong answers. So here is a nice example from a paper in prep from one of my collaborators. So what he's doing here is looking at the total mass in gas in his simulations as a function of time in the hydrodynamic case, which is the red curves, and the MHD case, which is the blue curves. And I want you in particular to look at the red curve. So just looking at the total mass in his repo simulation represented by the mesh cells as a function of time, he sees this big drop over time as stars form. But actually, this is not all accounted for by star formation. Star formation is actually only about 10% of this drop. Most of this material is stuff going into the sinks and getting trapped there that will eventually, when those sinks are removed from the simulation, will eventually get recycled. And you can see this if you account for that gas trapped in the sinks, you get a much lower drop in mass as a function of time. So if you're using this sync particle approach and you want to compute things like the depletion timescale, then it's important to worry about this. If you don't, you can get very, very incorrect answers. Star particles don't have this problem because by construction, any gas which is not forming stars in the star particle approach stays on the grid. The problem they have is that this means that you sometimes don't remove the gas fast enough and allow it to collapse up to very high densities, and then your simulation grinds to a halt. So trade-offs, always trade-offs. Advantages of star particles, they're lightweight. You don't need to store much information, the mass, the age of the stars, the position and velocity. And once you form them, because they're only really interacting via gravity, they don't have to do much communication. So they're pretty good at scaling to very large numbers of particles or very large simulations. The disadvantages, as I say, they're not always effective at preventing gas from collapsing beyond the resolution limit. If your criterion for forming them or your algorithm for how quickly you form star particles doesn't keep up with how quickly the gas is collapsing, then it can just wind up at very high densities, and then you have a problem. Now, sync particles, these are generally the best choice for very small scale simulations, so of individual clouds or clusters, because they really do allow you to follow the actual mass growth and evolution of other quantities like the angular momentum at the real stars are going to accumulate during their pre-main sequence phase. However, on larger scales, we have a bigger problem, because using these in galactic scale simulations, you generally don't want to assume that all of the gas going into a sink will form stars. That will give you far too much star formation. If your sink is representing gas, for instance, which is at a number density of 10 to the 3, a lot of gas in GMCs at number density of 10 to the 3 is never going to form stars. So if you put it all into stars, then you get too much star formation. So then you have this gas trapping problem. The other problem with sinks is because they're still accreting from the grid, you need to do a lot more communication. They need to be aware of the gas distribution around them so that they can figure out whether or not to accumulate gas from those grid cells. they also need to be aware of where the other sinks are, because if you have two sinks close together, you need to be able to figure out, okay, does my gas cell get accreted by this one or that one? There's a much higher level of communication needed. And so in practice, sinks don't scale very well for very large simulations. It's very easy to write sinker algorithms in a way where you're doing operations which scale as the product of the number of sinks and the number of gas cells, which when you're dealing with a few hundred sinks is fine, and when you're dealing with 10,000 sinks is not fine. This is something that we've encountered in our own work, and yeah, what works well for individual clouds often breaks badly when you scale it to entire galaxies. Okay, so the next physical ingredient I want to talk about is cooling. Strictly speaking, cooling and heating, but we're mostly going to talk about cooling. Now, we know that the ISM contains gas with a huge range of temperatures. There's this common idea of like splitting it up into thermal phases, the molecular gas, the CNM, WNM, the hot ionized medium. And together, these things span 6, 7 orders of magnitude in temperature. And at some densities, we see gas being quite close to thermal equilibrium, but at other densities, we find a lot of scatter in the temperature at a given density. So we can't just assume always that we have a well-defined thermal equilibrium state. Non-equilibrium effects are often important. And so generally, we actually need to solve the evolution of the temperature. So this is an example taken from real galactic simulations. So these are two temperature density curves for simulations by Chelgun et al. So this top one is for all of the gas in the disk of the galaxy, and this is for just gas at the galactic center. So we see at high densities, you mostly have cold gas. At intermediate densities, there's a bit more of a mix. So you have a lot of gas sitting around 10 to the 4 Kelvin, where atomic hydrogen cooling becomes ineffective. And then we have this region at low densities and very high temperatures. So this is all of the material that's been shock heated in supernovae. And clearly, this material is not in thermal equilibrium. At any given density, we have several orders of magnitude difference in the temperature, depending on what has happened to those gas cells. They've just been shock heated, they're at high temperatures. If they've had a chance to cool, they're at low temperatures. At this end, we see a better equilibrium curve, particularly as we go out in the disk, because the cooling time is quite short compared to the dynamical timescale. In the galactic center, the dynamical timescales are also short, and we see, again, non-equilibrium effects becoming more significant. See hands-on project number 9 if you want to generate these curves for yourself. We also see similar effects inside individual GMCs. So this is from a calculation I did a while back, looking at a turbulent GMC. So at low densities, we have a fairly tight density temperature curve because it's set primarily between the balance of photoelectric heating and C+ cooling. But once we get to these densities, we're sensitive to exactly how much visual extinction we have. We're also sensitive to the local velocity field because we're dominated by CO cooling, and that depends on the local velocity divergence. And so we get this big scatter. And then at very high densities, essentially, dust cooling becomes dominant, and the gas temperature just winds up tracking what the dust temperature. And it's quite common to approximate this by assuming what we call collisional ionization equilibrium. So basically saying, okay, my ionization state is set by the balance between collisional ionization and radiative recombination. And the nice thing about that approximation is that both of those processes scale in the same way with the density. They're both density squared processes. So that means that my ionization balance, hence my chemical state, and hence my cooling rate, all become pure functions of temperature. So you can just calculate them ahead of time as a function of temperature, and then just do a temperature lookup. So this, if you do that, you get this gray curve here. So this is from some calculations by Nathan Ferland. So the gray curve is the total CIE cooling rate coefficient. So you multiply this by the square of the density to actually get the cooling rate per unit volume. And then what they also show in this plot is how this breaks down into the contributions of individual elements. So this peak at low temperatures is due to Lyman alpha cooling from hydrogen, but then we have this much broader peak at temperatures between about 10 to the 5 and a few times 10 to the 6 due to metals, so primarily carbon and oxygen, but also significant contributions from neon and iron. And then as we go to very high temperatures, we lose pretty much all of the metal cooling because everything is fully ionized at this point, and we wind up just being dominated by Bremsstrahlung involving hydrogen and helium. Okay, so this is very commonly done, but the problem is that actually collision ionization equilibrium becomes pretty ropey when we get down to temperatures close to 10 to the 4 Kelvin, because the chemical equilibrium timescale is often much longer than the thermal timescale. In other words, our gas cools or heats up faster than the ionization state can respond. So it doesn't do a good job of modeling cooling when the cooling time is short. It also doesn't do a good job of modeling cooling if we're not in a state where collisions are dominating our ionization state. So if we're in an H2 region and we're dominated by photoelectric heating, then assuming CIE is the wrong thing to do. It will give us the wrong cooling rate. So although this is a commonly adopted approximation, when you actually look at it in detail, it doesn't do great, particularly for stuff close to 10 to the 4 Kelvin. Now, one simple improvement is just following the ionization state of hydrogen explicitly and only doing CIE for the metals. So that gets rid of this peak at low temperatures, which typically you don't have in non-equilibrium calculations. At a bit more cost, because now you have to do a bit of chemistry, but if you're only doing the hydrogen chemistry is pretty simple. So it's not much cost. You can also, to deal better with H2 regions, you can compute equilibrium curves for photoionized gas and for collisionally ionized gas and interpolate between them depending on your local condition. This is, for instance, what is done in the TGRES simulations. So this is a very complicated plot, most of which I'm not going to explain. But basically, the solid line here is the cooling rate they expect in the CIE case. The dashed line is what you get for the photoionized case. And so they've pre-computed these two things. And depending on whether they're in an H2 region or not, they either follow the solid line or the dashed line. So at high temperatures, they just assume CIE anyway. But at low temperatures in H2 regions, they have less cooling than if that gas was shock heated. In terms of the overall dynamical response of the gas, doesn't make that much difference. In the end, the cooling rate is dropping sharply enough at low temperatures that this makes a few thousand Kelvin worth of difference, which is like a 10 to 20% error in the thermal pressure, which is important, but not like game-changing. So your overall simulation is probably not going to run too badly wrong if you're just using CIE everywhere. Where this becomes an issue is comparison to observations. If you're trying to model something like the optical line emission from H2 regions, there, though, that 1,000 or 2,000 Kelvin of difference really does make a big difference, for instance, for predicting how much N2 or O2 or O3 emission you're getting. So often doing it right is not so important for getting the simulation to behave and to form stars at the right rate, but it is important for the comparison to observations. Okay, so that's the high temperature end. Now, the low temperature end, things get more complicated. This is from one of my own simulations, just showing the different thermal processes dominating. So at the very low densities, we're dominated by C+ cooling. This is this blue dashed line, which you can see kind of falling off here. And photoelectric heating, and then intermediate densities, you're dominated by CO cooling, and then the highest densities, it's compressional heating and cosmic rays and dust are the main processes. In general, in this low temperature regime, we need to worry about atomic fine structure lines, we need to worry about molecules, and we need to worry about dust. Now at solar metallicity, the molecular cooling is not so important. CO actually only dominates for about an order of magnitude in density. So we don't go too badly wrong by ignoring it and just assuming we just have atomic fine structure cooling, and at the highest density is just dust cooling. You make a small temperature error, but overall your simulation still produce stars at a reasonable rate. And again, at solar metallicity, H2 cooling is almost never significant because the gas cools down quickly enough to temperatures where H2 cooling is too slow. Now, this is not true at low metallicity. If we're interested in modeling the low metallicity in stellar medium, so in very low metallicity dwarf galaxies or galaxies in the early universe, then we get into a regime where you start being dominated by H2 cooling. And this is nicely illustrated in this plot from Bialy and Sternberg, where they're showing as a function of metallicity and density what cooling processes dominate. So you see that there's this region dominated by fine structure cooling, which at high metallicities pretty much dominates above a number density of a few. So in the CNM regime, and then at lower number densities, you're dominated by Lyman alpha cooling. And down here, there's not much dependence on metallicity. But then as we go to lower metallicity, at low densities, you're still dominated by Lyman alpha. But at higher densities, you start getting into this regime where you're actually dominated by H2 cooling. And so if you ever want to model things around about here, these very low metallicity systems, you'd better have some treatment of molecular hydrogen in your simulation. So, properly modeling cooling in this regime, in this low temperature regime, does require some treatment of the chemistry. At the very least, we need to know what our carbon and oxygen are doing so that we can get the fine structure cooling right. At low metallicity, we also need to worry about this transition from H to H2, so we get the H2 cooling right. And many models do not do this, with an unclear impact on the dynamics. Now, getting this right is definitely going to be important if you want to make direct comparisons of atomic molecular emission with observations, because even if you're only making small temperature errors in something with an excitation barrier of like 50 or 100 Kelvin can make big differences in terms of how much emission you actually get. How important this is for like the overall dynamical behavior of the simulations is less clear. Okay, now this brings me on to the topic of chemistry. So just given one reason why we need to worry about chemistry. Of course, we might also worry about chemistry because we're interested in chemistry. We're interested in understanding the chemical makeup of the ISM. I mean, after all, a lot of what we observe in terms of observational traces is molecular line emission. So we need to know where those molecules come from. And something we know is the ISM is very chemically rich. There's well over 100 molecules have actually been detected in the ISM. Astrochemical models tell us there's far more than that. It's just like there's a limit to how many you can actually identify. And state-of-the-art models of this chemical complexity can easily contain many thousands of reactions. So great, right? We just take all of that, plug it into our simulation, done, right? No. Doing all of this in a 3D simulation is completely impractical. And the problem is that chemical rate equations are what's called stiff. So what I mean by that is if you have a coupled set of ODEs that are stiff, they contain multiple different characteristic timescales, which have very different sizes. So you have some components of your solution which change on very short timescales and some components which change on very long timescales. And what this means is that you cannot solve these ODEs explicitly, i.e. going forwards in time, unless you take extremely small time steps. Because if you try and do it with a large time step, you're dominated by these these components of your solution varying on very short timescales, and you find that your solution is unstable. It just blows up. So to solve this explicitly, you have to take extremely small time steps, which is impractical, or you solve it implicitly, i.e. iteratively, which can certainly be done. There's a lot of fairly sophisticated solvers to do this, but then you have the problem that this kind of iterative implicit solution has a cost which scales as the cube of the number of the species that you're dealing with. So for a small number of chemical species, that's fine. That's not too bad. For 100 or more chemical species, that's catastrophic. So you can easily do this in one zone or even in 1D calculations, but scaling to 3D calculations where you're having to do this for hundreds of millions of gas cells is really hard. So what most people do, what I built half my career doing, is use what's called a reduced chemical network. And the idea is to just follow in the simulation the chemistry that you have to follow. So I would argue just basically what's vital for getting the cooling right. And this will typically be a pretty small subset of the full chemistry. So if you're going from like 100 species to 5, that's a factor of 20 cubed speed up. That's pretty good. And then just worry about doing the rest of the chemistry later. You can model the rest of the chemistry with post-processing as long as during the simulation you save the right information. Now, this is something I don't really have the time to go into detail about, but basically the right information here is for a set of Lagrangian fluid elements, the density, temperature, angled average, extinction, and things. And you can, if you're putting in Lagrangian tracer particles into a simulation which are recording this information, then you can later use that information to post-process your chemistry and get like the results you would have gotten if you had followed the full chemistry from the start in the simulation. If you want to know more about that, come talk to me later. Okay, so staying on this topic of reduced networks, there are various simple networks available. The simplest thing is just follow hydrogen, so the ionization balance and H2 formation. We can do a bit better by following the transition from C+ to CO. So there's a really simple approximation that Nelson and Langer introduced, which basically models this with one rate equation, with the disadvantage that you say nothing about atomic carbon, you just assume C+ magically turns into CO with nothing in between. Or there are more complex versions of this. They a couple of years later published a more complicated network, which does a lot better. And then Munan Gong back in 2017 improved on that further and made it more accurate when, for instance, the cosmic ray ionization rate is large. So right now, if you want something fast, I would suggest using this one. If you want something accurate, then use this one. I think on grounds of time, I'll skip over that. Something else you need to be aware of is that accurately modeling the molecular chemistry of GMCs in large simulations of the ISM needs high spatial resolution. If you don't have enough resolution, you don't properly model the density structure of the clouds, you're going to get the wrong chemical composition. So in that case, it's not worth spending the cost of a large detailed chemical network if you're just going to get things badly wrong anyway because of limited resolution. So this is just an illustration of this from this paper by Daniel Seyfried. So this is for two clouds formed in a half kiloparsec by half kiloparsec patch of the ISM, where they're zooming in on these clouds with different maximum resolutions. So this is actually a bunch of different simulations where they limited the maximum resolution to different values. So the light blue line you can just about make out is like the finest grid was 4 parsecs, and then the different colors as we go up from there, you're making the finest mesh cell finer and finer and finer till the smallest one is 0.06 parsecs, which you'll notice doesn't go all the way to the end of the plot because that was so slow they couldn't afford to do it all the way to the end. And the key point is that you see the amount of H2 in this panel, or CO, is sensitive to that grid resolution, particularly at low resolution. There's a huge difference between how much molecular gas we make when our minimum grid cell size is 4 parsecs versus 1 parsec. And then as we make the grid finer and finer, we still see a resolution dependence, but that resolution dependence gets a lot smaller. So at some point you can say, okay, this is good enough. So formally, you need to actually go to about 0.1 parsec resolution to get numerical convergence. In practice, 1 parsec, about half parsec, is probably okay. But if you're running a simulation where your minimum resolution element is like 4 parsecs or 8 parsecs, which is quite common, then yeah, then you're going to be getting the chemistry wrong. And then it's not worth worrying about using complex chemical networks because you simply don't have the fundamental resolution to make use of them. Okay. Next topic, stellar feedback. If I was talking about star formation, I would talk at this point about protostellar jets because they're important on small scales, regulating what's going on inside individual molecular clouds. But on the large galactic scales we're primarily interested in, they're not really important. They're very localized. So on large scales, we're mostly interested in feedback from massive stars. So winds, radiation, and of course supernova explosions. And if we look at the overall energy budget, so this is just from a starburst 99 calculation for a solar mass star. This is the bolometric luminosity as a function of time. So while our most massive O stars are on the main sequence, this doesn't vary much with time. And then, of course, once our most massive stars start dying, this starts dropping off quite significantly with time. The blue line gives us our wind luminosity, which at very early times is pretty constant, and it picks up towards the end of those massive stars' lifetimes as we reach the Wolf-Rayet phase, and then again drops at later times. Only there it drops off much more rapidly because much more of that wind energy is just coming from the very most massive stars. And then finally, the supernova energy input averaged over time is of course 0 until we start getting supernovae, and then we have lots of energy at the start, and then a relatively flat evolution until our least massive B stars have exploded as supernovae, following which nothing much happens. Okay, so there's lots of energy available. And in principle, we need to worry about all 3 of these different forms of feedback. Now, the one that's most commonly dealt with is supernovae. Pretty much any large-scale simulation of the ISM, which is doing star formation, will have supernova feedback in, because if you don't have some form of feedback in, and supernova is the easiest one to put in, then you just form all of your gas in stars very quickly, and it's not very realistic. So having no feedback is not good. So putting in supernovae is the most common thing to do, and the simplest way to model supernova explosions is to just dump in thermal energy to represent the energy released by each supernovae. So basically, dump in the thermal energy that we expect each supernova remnant to have in its set-off-Taylor phase. So if you do this, you face an immediate problem that if the local gas density is high, then that energy just gets radiated away before the gas has a chance to respond to the high local thermal pressure. So before the pressure can force the gas to expand and go to low density, it just gets radiated away. You get what's called overcooling. And this leads to very inefficient feedback and excessive star formation. And fundamentally, this is a resolution problem. If you had higher numerical resolution, finer grid cells, you wouldn't have this problem. So we get around this by basically looking at whether we have enough resolution to properly resolve these highly energetic supernova remnants. And the key quantity here is the size of the remnant at the end of its set-off-Taylor phase. So at the point where the evolution stops being adiabatic and radiative cooling starts becoming important. Now this can be predicted as a function of steam temperature. It's a relatively simple function of those quantities. And so we can just compare this radius with our resolution. And if we're well resolving this set-off-Taylor radius, then we're not going to get overcooling because the gas will have had time to respond to the influence of that energy and rearrange itself. And so it will have a realistic density distribution at the point when cooling becomes important. On the other hand, if we're not resolving this set-off-Taylor radius, then essentially we'd be dumping that energy into dense gas, which doesn't have time to respond. And so we'd have overcooling. And so we avoid that problem by, instead of dumping in energy, just working out what the momentum should be at the end of the set-off-Taylor phase and just dumping in the momentum instead. Because of course that kinetic energy can't get radiated away. So this kind of switch between energy driving and momentum driving is quite commonly done. When we're running with chemistry, we also need to think about updating the chemical state of this gas to be realistic. If you don't do this, then you get ridiculous things like molecular hydrogen at 10 to the 6 Kelvin, because what has happened there is you've dumped in a supernova and you've written a snapshot immediately afterwards before the chemical module has had a chance to say, oh, all of my H2 should have dissociated practically instantly. So normally these days people are aware of this, but it is something to be aware of. Okay, so when can we actually do energy driving? When can we do momentum driving? So I just made a little plot here showing the set of Taylor radius as a function of density for solar metallicity gas. So these are the sort of densities we typically find within GMCs. So you see, to represent supernovae properly on these scales, we actually need to resolve scales of a few parsecs. So we need grid cell sizes or resolution element sizes of a parsec or less. And if we not reaching that resolution, then we're not going to represent things properly on these scales if we're dumping in energy, and then we have to dump in momentum. This plot also shows that we have an issue if we have supernovae exploding very low density environments. Because something that's quite commonly done is to just say, okay, we're just going to inject our energy within a sphere of radius R set of Taylor, which is fine for things that are exploding in the warm, neutral, or warm ionized medium, because then you're putting things into a radius of like 20, 30 parsecs, which is about the size of an evolved supernova remnant. It goes badly wrong if you're exploding things in very low density environments, for instance, in the middle of superbubbles, because then our set of Taylor is a few hundred parsecs. And your supernova remnant is never actually going to reach that scale. That's bigger than the scale height of the disk. So if you're not careful and just blindly put in energy into this scale, you can basically start putting energy in essentially over very large scales in cases where you don't really mean to. Now, this issue gets a lot worse in Lagrangian codes. You need to be a lot more careful of this in Lagrangian codes because they inherently have lower spatial resolution at low densities because there's little mass there. So unless you actually limit the code and don't let it derefine in low density regions or force it to keep some minimum or some maximum resolution element size, you can wind up with very large grid cells in those low density regions, and it can be difficult to do the energy injection properly. Okay, I am running short on time, so I'll skip that. Another issue with supernovae, we need to decide where we inject the energy and momentum. Do we do it completely randomly? Do we do it in a way that's clustered with the sinks or stars, but still somewhat random? Or do we do it right on the locations of the star particles? And it turns out the choice of what we do here makes a huge difference to the effectiveness of the supernovae, because it controls the density distribution in which the supernovae explode. If we have clustered supernovae, so we make sure that our new supernovae are occurring close to where the old ones did, then most supernova explosions will happen in low density regions. And then you get much more effective explosions. You get much less radiation of energy, you get more momentum deposited, you get more disruption of the disk. Now, so much for supernovae. Now, what we also know is that if you just have supernova feedback, you don't get an ISM that looks like the real one. You get too much hot gas, you get too much cold gas, you get too much star formation, and you get clusters which are too big. And all of these problems stem from the same root cause. You get too much gas collapse and star formation. And this occurs because you have an inherent time delay in when this feedback starts operating. You don't get any supernova feedback till you have your first supernovae, and those don't happen until your first massive stars have died. So in between when star formation starts and when the feedback starts is a difference of like 3 or 4 megayears. And so if your cloud is forming stars rapidly, then it can form a lot of stars in that time. You can do a lot of collapse in that time. And then once your feedback is starting, you've already made big star clusters, you've got lots of stars. You've also collapsed a lot of your gas into low volume, high density clumps, which are difficult to disrupt. And because a lot of your gas is in these cold dense clumps, then you've got a large volume of lower density material which you can heat up very easily. So you get a large volume of hot gas. So the solution to all of these problems is to have some form of feedback that happens faster. So what we call early feedback. Basically, some form of feedback that happens as soon as we start forming the stars. And the leading candidates for this are either stellar winds or ionizing radiation. Now, the question of which form of early feedback actually is most important is something that observers are trying to answer. I'm not going to talk very much about this because this is something Anna is going to cover in her talk. But basically, to very briefly summarize, we know on small scales, winds and radiation pressure seem to be the dominant things, whereas on large scales, we're primarily dominated by just the thermal pressure of ionized gas, with winds and radiation being somewhat less important. Okay, so how much difference does this make in a real simulation? Well, people have done comparisons of this. So this is from a study by Rathjen et al., where they're basically looking at what happens as you switch on different combinations of feedback processes. So S here just stands for supernova, R is radiation, i.e. ionizing radiation, W is winds, and then C is cosmic rays. So in some of his simulations, he also has the supernovae acting as sources of cosmic rays. So you see, when you just have supernovae, you get too much star formation. You get an ISM which sits well above the Kennicutt-Schmidt law. So this is where actual spiral galaxies should sit. These background points are real observations. If we turn on some form of feedback, some form of early feedback, either in the form of radiation or winds, then we move much closer to the actual observations. And if we turn on both together, or even better, also switch on cosmic rays, then we move even further down. In fact, with cosmic rays as well, you tend to underproduce things. But with just winds and radiation and supernovae, you're pretty close to where the observationally determined points are sitting. You also, if you look at the cluster mass distribution, so with just supernovae, you get clusters which are far more massive than the actual observed distribution. Whereas once you switch on something like radiation feedback, you get distributions which much better represent what the observations actually show. And also, if we're looking at the phase balance, so the amount of hot gas or the mass fraction of cold gas, so this right-hand column here is the actual, what we observe in the Milky Way. And you see with just supernovae, you get too much cold gas, too much volume filled by hot gas, whereas with proper treatments of early feedback, you get something that much better represents what the galaxy is actually doing. So we get the best match to observations when we include all forms of feedback. Even if this isn't practical, then you should at least put in radiation. If you really can't afford that, or your simulation doesn't include it, then supernovae aren't terrible. But you need to then be aware that, yeah, you will probably be forming too many stars and having some of these other subtle issues. Okay, how much? 5 minutes. Right, there, I will not talk about cosmic rays. Cosmic rays are cool, but there's no time to talk about them. I will very quickly talk about a few examples, and then I have a few slides at the end I want to talk about things we need to think about for the future. So just 3 examples. I could spend another half an hour talking about different projects to simulate the galactic scale ISM. I've just picked out 3 that I know fairly well. So one is Tigris NCR. So these are MHD simulations of a representative patch of the ISM. So they take a 1 kiloparsec by 1 kiloparsec patch in the disk in some tall box, so you can represent gas flowing above and below the midplane. And these simulations are done with Athena, which is an Eulerian grid code. So these are not actually AMR, these are fixed grid. And they're using what's called shearing sheet boundary conditions. The idea is that the boundary conditions are representing for the fact that this box is actually in a rotating disk. They have pretty detailed treatment of cooling chemistry. They have supernovae, they have stellar radiation, sync particle-based star formation, and they make results that look quite like this. So you see you have a good representation of GMCs, of ionized regions with bubbles of hot gas, most of the volume being filled with warm gas, and then these denser GMCs. Another fairly influential model is the Silk model. So this is the same idea of just looking at a small patch of the ISM. In this case, they're taking just a half kiloparsec by half kiloparsec patch and modeling this with Flash. Now, Flash is an AMR code, so they have the advantage that they can potentially zoom in to much higher resolution than Athena can afford. And the other big difference is they have a fairly sophisticated treatment of feedback. So the latest Silk simulations have supernovae, winds, radiation, and cosmic rays. Not sure about radiation pressure, but it's probably not important on those scales. On the other hand, they have a much more simple chemical network compared with Tigris. I'll skip over that, even though it's a nice picture. And then the final project I just briefly wanted to mention is one I'm involved in called RHEA, where we're doing whole galaxy simulations using a repo. So this is a moving mesh approach. These simulations only have feedback from supernovae. We have a pretty detailed cooling treatment, very simple chemistry treatment, no early feedback yet, but self-consistent cosmic ray transport. And you've seen this plot already. Okay, so if we compare these different models, we can get some sense of the trade-offs you have to make. So Tigris does a bigger volume than Silk at comparable resolution. It does better boundary conditions, it has better radiative transfer, but it doesn't have cosmic rays. Silk has a more comprehensive treatment of the physics at the cost of doing the radiative transfer in a more approximate way. Something like RHEA has a much, much bigger volume. It's modeling like the entire disk rather than just a small patch. And this allows you to do things with these simulations that you can't do with the small box simulations. For instance, you can look at the large-scale morphology of the Milky Way. You can look at the influence of the bar on the center. But it's got much worse spatial resolution, particularly at low densities. And at the moment, it doesn't have early feedback, although this will come soon. Okay, and if you want to know more about any of those or any of the other projects that other groups are involved in to try and model the ISM, just come talk to me. Now, in my 1 minute, I will try and talk about a little bit about the future. So, as I wanted to just like briefly indicate with the examples session, there's a lot of codes that implement most or all of the physics that we need to model the ISM. There's a lot of different algorithms and approximations, many of which I've talked about so far today. And we want to know how consistent the results are from different codes. So there have been a few studies on this. So Coleman last year compared simulations of the ISM with 3 different codes covering different scales and looked at the properties of GMCs formed in these codes. And one problem was that the simulations actually covered such disparate scales, they often didn't overlap very well. But if you did plot the different mass functions, then in the regions where you actually got overlap, where the simulation had enough resolution or enough volume to properly represent what was going on, you get reasonably good agreement. You get very good agreement on things like cloud shapes, and also on the things like the line with size relation. Again, there's not much overlap between different simulations, but where the simulations overlap, there's not much offset from one to the next. You got much worse agreement on something like the temperatures. So these are the temperature distributions of the gas flagged as being in clouds. Now, clouds in this sense are not necessarily GMCs. And you see that some codes just had relatively cold gas and some had very hot gas. However, on the whole, Coleman et al. Found reasonably good agreement between different models. On the other hand, Hu et al. Did another comparison a while back between GISMO, Aripo, Gadget, and Ramses with the same cooling module used in all 4 simulations, the same star formation algorithm, and the same feedback algorithm, and just looking at how this interacted with the different way of doing the hydrodynamics. And what they found is that at high resolution, you could get quite different behavior. In fact, in the Lagrangian codes, you got much burstier star formation than in the Eulerian code, in the Ramses case. In Ramses, at high resolution, you get this relatively stable star formation rate, and in the Lagrangian codes, you got this very bursty star formation. Now, this Hu et al. Basically attributed to differences in the density of the gas in which the supernovae were exploding. In the Lagrangian case, because you had much worse resolution at low densities, you tended to get the density quite different than in the Eulerian case, and this made a big difference to the effectiveness of the feedback. So there's at least one study saying, oh, these different approaches agree fairly well, and another study saying, no, actually they agree quite badly. So basically, we don't know. Is this difference in conclusions due to the difference in objects simulated? The Coleman et al. Were basically looking at an environment representative of massive galaxies like the Milky Way. Hu et al. Were looking at a dwarf galaxy, which has a much shallower potential well, is much more susceptible to feedback. Or is it due to differences in how star formation and feedback were treated? I think the main point to take away is we need people to do a lot more work on this. We need to understand to what extent different models actually do agree when they're trying to simulate the same things. I think people have spent a lot of work over the last 10 years implementing these capabilities, but we don't yet have a good sense of what you can actually really trust. Not in the same way that, for instance, for PDR codes, I think we have a much better sense because of the hard work done 10, 15 years ago to benchmark these against each other. Okay, I'm almost done. I know I'm over time. 2 more things to worry about in the future. And there's only 1 slide for each of these, so we are really almost done. So at the present time, running Galaxy scale simulations on tens of hundreds of CPUs is more or less routine, but this is still small compared to current state-of-the-art tier 0 supercomputers, which often have 10 to the 4, 10 to the 5 CPUs. So can we scale to that number of CPUs? And more importantly, what do we do in the future when new machines come along, which are mostly going to be GPU-based? Do we need to worry about porting things to GPUs to really make use of these exascale capabilities, or do we just stick with these relatively small scale simulations? I don't have an answer to this. It's something I think as a field we need to figure out an answer to, but I don't actually know what the right strategy is for the future. And last slide before the summary, just because I had to get some machine learning in here somewhere. So can artificial intelligence help us? In principle, you could imagine training a neural net to emulate an entire ISM simulation. In principle, there's no fundamental reason why you can't do this. In practice, it's not going to be practical to do this because it's so costly to run the simulation, you cannot run it enough times to generate a suitable training set. Yeah. So just trying to emulate your entire simulation with AI, I think in the near term is not realistic. However, what we can try and do is extract bits of that simulation and emulate those and try and replace the costly bits of the simulation with emulators that give us the same answer for a fraction of the cost. And so one region in particular that's attracted a lot of attention is doing this with chemistry, because that's pretty separate from everything else the code is doing. So you can basically try and train an emulator to basically say, okay, given these chemical abundances and density and temperature and radiation field strength, what should my chemical state be at the end of my time step? And the results here are pretty promising. So this is from a paper from last year by Branco and Palatini, looking at a pretty simple chemical model. So this is just primordial hydrogen-helium chemistry. The solid lines are the results of the real simulation solving the chemical rate equations. And the dashed lines are from the emulator. And it's pretty good. It's pretty good. It's not yet at a state where we can think about replacing what we're doing in the numerical simulations, but I think within half a year to a year, we could actually try putting in an emulator into a full 3D hydrocode and see how it gets on and like really benchmark it against doing it properly and see whether you get reasonable outcomes or whether you find that once you go to this very large simulation, you start exploring parts of parameter space which were not in your training data and you start extrapolating and getting nonsense. How well this will work in practice remains to be seen, but I think it's a very promising avenue for at least speeding up chemistry, which can often, if you're doing lots of chemistry, if you're doing these sophisticated chemical networks, this can be the dominant cost. So if you can make this take a fraction of the time, this is a big win. Okay, so a few points to take away. State-of-the-art simulations of the galactic scale ISM contain a lot of different physics. I've tried to summarize the most important things here. There are things I ran out of time to talk about cosmic rays, and there are other things like dust or like thermal conduction I've not had much time to talk about at all. There's lots of different ways we can try and simulate these with different strengths and weaknesses, and it's important to understand the trade-offs that we're making. Both if you're interested in running these simulations yourself, but also if you're interested in just using the output or like comparing your observations to the predictions of simulations, I think it's important to understand a lot of the trade-offs that are being made, the approximations that are being made, what you can and can't trust. We're often not good enough as numerical astrophysicists to spell this out in papers. So it's often a good idea to come talk to the people actually running the simulations. Like, yeah, can I trust what this is telling me for the temperature of the ionized gas? Like, no. So, and finally, I think two important things for the future, for the next generation, more and better comparisons between models, getting a much better understanding of what we can trust and what we can't. Of course, you still have the issue that even if all of your models agree, that doesn't necessarily mean that any of them are doing the right thing, but at least it gives you more confidence that they are. And then finally, how do we deal with a GPU-dominated and AI-dominated future? So, thank you.
Much, Simon. In principle, we have 1 minute. How many questions may I allow? I'm looking at the stock and 2. Okay.
Well, I'll be around for the whole of the school, so you have plenty of time to ask me later.
Thank you for the great overview. Would you mind going to the couple of slides before the star formation section? So if I understood correctly, you showed some runs in which the choices you made impacted gas morphology a lot, but the star formation rates were still similar for those runs. And having a very gas-centric view of star formation where like gas density and how it's bound impacts star formation a lot. I was just confused about how it makes sense for these runs to have different morphology for gas, but similar star formation rates.
Yeah, well, this is something we've not just found in these simulations, but also other work that Robin Tress has done looking at something like a M51 analog, where when you have a flyby with from a companion, you get a big grand design spiral arm, and in the other case, you don't. And in both cases, we got pretty similar star formation rates. And basically, the issue seems to be that what is primarily controlling your star formation rate is how much dense gas you have and not where it is. Like if you have about the same amount of dense gas, it doesn't matter whether it's spread through the disk in a flocculent spiral or it's in some grand design spiral arm. you still get star formation at about the same rate. And it's basically because star formation seems to self-regulate. So you can redistribute the gas within reason and not really change the efficiency with which you're forming stars. And I think there's a lot of observational evidence that this is the case. You can also, if you look in the Milky Way and really carefully try and measure star formation efficiencies in clumps on spiral arms and off spiral arms, you don't really see a difference. So I think what the simulations, and I'd argue also the observations, tell us is like spiral arms have lots of stars because that's where there's lots of gas. It's not because they're actually any more effective at forming stars. It's just that's where the gas is. And if the gas is somewhere else, it still will form the stars at about the same rate.
So the density profiles of the gas was still like similar across the
Yeah, I mean, this is talking about the large scale morphology. Of course, if you zoom into individual clouds, then the density structure of those clouds will make a difference. But I think the point is the density structure of the individual GMCs doesn't know much about like the kiloparsec scale morphology of whether those GMCs are in a spiral arm or in the interarm region.
Thank you.
At least to a first approximation.
Thank you for the nice overview. So I have a question regarding the gravitational smoothing. So I'm not an expert. I found that interesting that you kind of start tweaking with gravity once the gas gets interesting, if I want to phrase it maybe very provocative. So I was wondering if there's any motivation behind, like a physical motivation behind this Plummer profile that you're choosing. I assume the problem of these high accelerations comes from that you're not really resolving like the inner structure of the mass particles. Yeah. But I can't see how that would lead to this solution that this is justified. So I was just wondering about that.
Yeah, so I mean, this was originally designed for n-body simulations. I mean, I should stress that most people use something more complicated than Plummer softening. It was just the easiest one to put in the slide. But yeah, in n-body simulations, you want to avoid getting very close encounters between particles and very high accelerations because that's going to be very slow. And if you want to model something like a globular cluster over a gigayear, you cannot afford to properly model those close encounters. So then they have a lot of tricks for what they do instead. In the case of the gas, that's less of an issue. You do sometimes still have an issue if you have sync particles. You're going to want to soften the gravity because otherwise when they start interacting, you can, again, have to take very small time steps just because you have strong scattering, which is unphysical in that case because those should actually be representing clusters of point masses, not behaving as individual point masses. So when they get very close to each other, yeah, the fact you're representing them in the code as individual point masses is actually wrong. And so the softening is in part a way to try and account for that. But also with the gas, it's just to avoid getting this unphysical behavior. If you don't soften the gravity, then on very small scales, you still have your full gravitational force, but you inevitably are softening the pressure force because you no longer, once you're down at the grid scale resolution, you're not able physically in the code to represent the pressure gradient. Yeah, within one cell, there's no pressure gradient. So if there's still a strong gravitational attraction from one cell to its neighboring cell, but you're not got the right pressure gradient because you've not got the resolution, then you're going to get the wrong behavior. So softening in the gas is primarily to deal with that problem, less so the accelerations. But the accelerations are still an issue when you have point masses like sync particles flying around. And in that case, it's because, yeah, those are unphysical. You should not have 2 10 to the 4 solar mass clusters behaving like point masses when they get close to each other, because they're not. They're actually extended objects, but just we're representing them in the code as point masses.
Let's take Simon again.